We're now going to look at case 3 concerning the stability of the solutions of this special second order differential equation. And what is case 3? That is this situation here where phi is someplace between plus and minus 1. Now I've already generated a solution here, and this is what it looks like. That's our first fundamental solution. In fact, that's our principal fundamental solution. And then this is our second fundamental solution. Remember, our procedure is always to start with a principal fundamental solution, and then from that construct a second fundamental solution that we can decompose into a periodic piece and a multiplier piece, let's call it. And that's what we're going to do in this case. Let's then look at what's happening here. Here's the significant fact. The modulus of each of these eigenvalues is 1. Is that an accident? No, that is has to be, and that follows from the fact that this phi is someplace between plus and minus 1. So let's explore that a little bit by looking at one of these. Let's look at this first eigenvalue. The fact that phi is between plus and minus 1 means that this thing here is negative. It's minus 0.98 in this case. So the square root of a negative number is imaginary. So I'm going to rewrite this. I'm going to reverse the inside. I'm negating the inside is what I'm doing. But I've got to put a minus 1 inside to reverse the negation. Or equivalently, I can put a I outside, and that gets me back to where I started. So this row and that row are the same. Now I'm going to take the modulus, or absolute value, of this thing, and in fact I'm going to square it. And since it has a real and imaginary part, I can get the square of the modulus by just taking the two pieces and squaring them. And now if I square the second one, it's inside the square root, so it's going to be just 1 minus Greek f squared in parentheses. And that, of course, is going to collapse to 1 if I simplify it. So let's do that. There it is. So that modulus is 1, and this one, the same argument on this side. The whole idea is that this phi squared here is something less than 1, or between 1 and minus 1. That lets us reverse it and come up with just a purely imaginary piece. All right, so what does that mean then in terms of convergence? Well, remember the property that our x has. Now our x here, our first step in generating a second fundamental set is to generate a solution in the old-fashioned way, the same way as before, and generate a periodic piece the same way as before. And then we're going to take those and move on with them. But remember the property that row 1 has. If you advance little t by big T, it's not periodic, but it throws out a row 1. Now this 9.98, I'd like to see a 1 there, but I didn't do enough precision over here. If I took a larger number here, I could get a better precision here. But in general, or theoretically, this should be true, that advancing t by big T just throws out a row. So then advancing little t by 2 big T's is going to throw out a row squared. Now in our previous two cases, that meant that this thing is going to diverge or converge. If the modulus of row 1 is greater than 1, then as you add more big T's on this side, you're going to add more exponents on this side. So this thing will diverge if the modulus is greater than 1 and converge if it's less than 1. In this case, though, the modulus is 1, so it doesn't diverge or converge. It just shifts xt around. It multiplies it by something, imaginary number on the unit circle, so it rotates it, but it doesn't distend it or contract it. So that shows that that we don't have divergence or convergence. Now, by proving that this thing is on the unit circle, I have effectively shown that this nu 1 has got to be 0. In other words, rho 1 can be written as just e to the I sigma 1 of t. This thing is on the unit circle. And if it had a real part up here, it would not be on the unit circle. Now in class he proved this a slightly different way, and let me try to do it that way. It's kind of interesting. So our goal now is to show that this nu 1 is 0. And let me repeat it. I've shown it's 0 because I've shown that the modulus of rho 1 is 1. That means that rho 1 is on the unit circle someplace, so its modulus is 1, and the log of 1 is 0, and that's what this thing is. That piece is the log of the modulus. If you look back at I think the second or first video, I went through a little complex arithmetic that showed you how that works. So I've shown that that is 0 one way. He shows it another way in class. Let me do that. Remember, this is something that he proved, that the cosh of mu 1 of t is phi. Well, another way of writing cosh is the cosine of minus I, either plus or minus. You can stick in there. Remember, cosine is an even function, so you can put a minus or a plus in there. They all come out to be the same. So that's the same as cosh. And the fact that phi is a number between 1 and minus 1 means we can take the arc cosine or the inverse cosine of both sides and end up with this equation. Now, why does that tell us that mu 1 has only a sigma 1 part and not a nu 1 part? That's telling us the same thing in a different way. Well, that's telling us that this thing, let's look at it. This thing here is real. I times mu 1 of t is real. And let's suppose that mu 1 had a real part. Let's do that substitution. Let's suppose that we rewrite that as nu 1, Greek in 1, plus I times Greek s1. Oh, that's not what I want. Is it nu? Okay, I gotta need a nu 1. See the value of having the tester there? All right, these are the same thing. In general, they're going to be the same thing, and in this case, nu 1, I'm going to show it has to be 0 now. So let's make that replacement. And if we expand all terms, and that I squared we can get rid of, or turn it into minus. I can't get rid of it. We can turn it into minus 1. I squared is minus 1. And now, suppose nu 1 were something other than 0. And this, let me put that by itself on one side, make it a little clearer. Okay, we have this here. So we have, if remember nu1's a real number and t is a real number, so this is purely imaginary, but this side over here is purely real. So there's a contradiction there. Nu1 has to be 0. So that's another way of showing that. Okay, so we've answered the stability question, I think. And now we want to come up with some real valued functions. Our problem is that everything we're dealing with so far is complex valued. Here's the x of t and the p of t. They both come out to be complex valued. It's pretty clear why. If v1 is complex valued, you look down here at the definition of x, our first fundamental matrix is real value times a complex number, so it's got to be complex. And the same thing with P1. It's not totally clear that it's complex, because it could be a complex and a complex and come out real, but it doesn't, as we can see over here. It also comes out to be imaginary. So how do we come up with real solutions? Well, what's the obvious thing to do? The obvious thing to do is to take the real part of x, and we call that xx, and the imaginary part of x, call that yy. They're certainly real, and they're solutions, because if the complex combination of the real and imaginary is a solution, then the pieces have to be a solution. So that is an obvious solution. And what about the real periodic solution? Well, we're being obvious here, so let's be obvious again. Let's just take the real and imaginary part of P. P is periodic. Our process that we went through is valid, and all we said before as far as periodicity is concerned is true. Even in this case, our only problem is our results come out to be complex. So the real part of a periodic function is also periodic, and the imaginary part is periodic. So we've got a new fundamental solution. We got a new x2, which is just, we just put together the real and imaginary parts of x. Pretty simple. We want to show now that we can decompose it, and we can decompose it into this thing. Remember, Q and R are just the real and imaginary part of P, of P1, in this thing. So the question is, where does this thing on the left come from? Now, I've convinced you, I hope, that nu1 is 0. I've carried along in the argument as if it weren't 0, because this argument is used in other places where it's not 0. At the very end, we're going to let it be 0 and show that this y is in fact a periodic function too. But let me carry it along for the time being. I did this ahead of time. It's kind of messy, so I had to set it up ahead of time. Well, what we're going to do is this. We're going to start with x of t, and we're going to extract its real part. That comes out to be this thing on top. And its imaginary part, that's the thing that comes out on the bottom. And that's going to be our new fundamental matrix. Now, the order that they are here is not quite right. This is actually a row matrix of the real part and the imaginary part. It's, we have one stacked on top of the other. Our solution is a column matrix of the real and imaginary part. So in some sense we're dealing with a transpose here, and that makes this a little confusing, but not if you keep it in mind. But let's first see how we get to this piece here. So we do that. We start with x of t, and we write it in terms of p1 and mu1. They're the same thing. Look over here. Same thing. And we're just using our definition of p1 and reversing it, essentially, to come up with this formula here. And now we're just going to break all the pieces up in terms of the real and imaginary. So, for instance, the mu1 we have defined the pieces of that to be, let me put this down here, the pieces of that are going to be, look at the formula form, it's going to be nu1, and that's 0, but I'm carrying it along just to make my argument general, times I times sigma 1. So just we've defined that to be true. Our tester confirms we haven't done anything stupid. So we'll replace that. And P1, remember how we define that? We define that as R and T. So let me do that. That's going to be Q of T. That's our real part of that function. And this is the imaginary part. So again, we define Q and R to make this true. Our tester confirms. I haven't forgotten what I set out as my definition. So let's make that substitution. All right, now what do we do? Well, what do we always do when we see E and a plus? We're going to split it up, but we have to first have to distribute that T. So let's do that. Expand all terms. We'll do that. And now we're going to distribute, or we're going to break up the E. So let's do that. Where is that? Here it is. Okay, and now what do we do? Let's do a factor all terms now. I want to do a factor all terms because I see this E sigma I of T. Remember there's a formula for that. E to the IA is cosine plus I sine. So I want to get that into the picture. Oh, what a mess. And now let's expand all terms. Okay, looks messy, but we got an I squared there. So that's going to simplify a bit. That's going to be minus 1. And now we got rid of all our I squared. So let's put it into imaginary form. If we do that, here's our imaginary piece, or starting here with its real coefficient, and here's our real piece here. And remember our goal is to split out the real and imaginary piece and use them as our new fundamental matrix. So let's do that next. And to do that, I want to put the real piece on top. So let me put that back here. And now for this second piece, I'm just going to push it down to the next row and get rid of the imaginary piece. And now I don't need my groupers anymore, so let's get rid of those. And let me do a simplify and see what that brings out here. Okay, well, I want to do a factor all terms, and that pulls E nu1 out. And now look at the inside. This here, this here is what I have up here. And if you look at it long enough, you can see it's certainly looks like it's coming from a matrix multiplication. Looks like we're multiplying QT from the right. We're taking QT as a column matrix over here, so to speak. Let me put that, imagine QT, imagine QT over here in a column matrix, a Q up top and an R at the bottom, and doing matrix multiplication on that, you're going to get something like this, where the matrix you're multiplying is what's left over. And that's not exactly what we want, though, is it? Because we don't want to multiply on the right with Q and RT. We're down here. We want Q to be on the left. Well, that's okay, because what we're talking about here is the transpose of what we want. If you look at our ultimate fundamental matrix, it's the same, or the transpose of that is the same as the thing that we're looking at up here. And the numbers confirm that if you look at these numbers here. So that, if you break this up into a product, it's going to be a row matrix, or another way of saying that, it's the transpose of a column matrix, which is what we want. So these are all equal. And so let's put them together here. And let's put it equals this second piece here. And see, the ones are, yep, we're okay there. And now let's hit both sides with the transpose. And use some properties of the transpose. The first one we're going to use is this one, say. And there it is. We end up with just what we want. We now have that x2 is this column matrix, which we are calling, this Q of t. And so this is the form of this column matrix. We're defining Q of t to be this column matrix, so our tester confirms that it's right. Let's look at back in decimal form. There it is. So let's go ahead and make that substitution. And that's it. We're done. We've decomposed x2 into a periodic piece. That's this first piece. And a multiplier piece. In our usual case, or the cases 1 and 2, the columns of this were multipliers with moduluses greater than 1 or less than 1, which cause divergence or convergence to 0. Here is actually a periodic function, and let's look at that with a little more care. So let's go down here. This is our y that we've broken out as a matrix. And let me put this in multi-line form. And remember, I told you that nu1 is in fact 0, but I wanted to carry this argument out to show you that how to do it in general. Is that what I want? That's not it. I want in there. Alright, so if I put that in there, notice what happens. Let me undo that. Nu1 is 0, then it's e to the 0, which is just 1. So let me do it again. And now we're left with a periodic function. It's a periodic matrix. All the pieces are periodic. The period is 2 pi over sigma 1, which is not the same as the period back here. Our period here was 2 pi over omega, whatever that happened to be. It's not sigma 1. So they don't have the same period, but that's not important as far as stability is concerned. This thing, both these columns are moving around the unit circle. Well, actually, they're not moving around the unit circle. They're moving back and forth between 1 and minus 1 in a periodic way. So the result is that this thing over here never diverges to infinity or converges to 0. So I think we're done, but let me just say it, the main point one more time. The fact that this is between plus and minus 1 means that the eigenvalues have modulus 1. And that we see down here always. That means, remember, the eigenvalues are the multipliers. They are actually called the characteristic multipliers. That means you're multiplying by a number which is essentially 1 over and over again. So you're not going to get convergence or divergence. And I think that's all we need to say.